We are going to learn one of the most important classical problems in data structures, which is called as Towers of Hanoi. This problem is very important because it helps us to clearly understand the recursion concept, which many students find difficult to understand. It also introduces us to the divide and conquer approach, where a big problem is broken into smaller problems. Through Towers of Hanoi, we will also understand how a problem is decomposed step by step, how recursive function call works, and how time complexity grows exponentially. This problem was introduced by Edward Lucas in the year 1883. He is a mathematician, and even today it is widely used in academics and interviews. Let us understand the problem clearly. We are given three rods, which is also called as pegs. A source rod, which is denoted as S, auxiliary rod, which is denoted by A, and the destination rod, which is denoted by D. On the source rod, we have n discs of different sizes. These discs are arranged such that the largest disc at the bottom and the smallest disc at the top. Our objective is very simple. We must move all the disc from source to destination rod, but we have to follow certain rules strictly. So the rules of this problem are, and remember one thing, we should not violate any rule. If we violate even one rule, the solution becomes invalid. The rule number 1 is only one disk can be moved at a time. We cannot move multiple disks together. The rule 2 is a disk can be placed only on top of a larger disk. This means a big disk can never be placed on a smaller one. Rule 3. Only the top disk of any rod can be moved. We cannot pick a disk from the middle or bottom. These rules force us to think carefully, and these are the reason why recursion is required. Let us understand this with an example of 3 disks. Initially, the source rod has 3 disks. The third disk is the bigger one, the second disk, and the first disk. So auxiliary, and we have 3 rods, 3 towers, or which is we can call it as pegs. So this is the source rod, this is the auxiliary rod, and this is the destination rod. The source rod has these 3 disks. The auxiliary rod is empty, the destination rod is empty. The disk 3 is the largest one and disk 1 is the smallest. Our goal is to make the source rod empty. The source rod is empty. The auxiliary rod should be empty. The destination rod should have 3, 2, 1 disk. So this is the destination rod. So which has to be in the same order of the source rod. So we are not changing the order of disk, we are only changing the rod. So the key idea behind the solution is the recursion logic. So this is the most important idea in Towers of Hanoi. Suppose we want to move n number of disks from source to destination. We cannot directly move the largest disk because smaller disks are on the top. So we have to follow these 3 steps. Move the top, let us consider the top as n minus 1 because we have n number of disks. So we have to move n minus 1 disk from source to auxiliary node using the destination as the helper rod. Step 2, we have to move the largest disk that is the nth disk, that is this is the nth disk, to the from source to destination. Then step 3, we have to move the n minus 1 disk from the auxiliary to the destination. Now the source rod acts as a helper. These same 3 steps are repeated again and again for smaller values of n. This repetition is exactly why recursion is used. So recursive algorithm for Towers of Hanoi. In recursion, every problem has 2 parts. One is base case, another one is recursive case. So we have a base case in recursive algorithm and we have a recursive case. So for every recursion algorithm, these are the 2 parts. So if a base case is, these 3 lines are for base case. If there is only one disk, then n is equals to 1. We can directly move the disk from source to destination. No further steps are needed. In recursive case, it means that if n is greater than 1, then we have to follow these 3 steps. First, solve the problem for n minus 1 disk. Then move the largest disk. Then again solve the problem for n minus 1 disk. So the meaning is we have to solve n minus 1 disk first. Then we have to move the largest disk. Then again we have to do the recursive function for n minus 1 disk. So the problem keeps calling itself with a smaller input. So let us see these lines, these 3 lines. So move the n minus 1 disk from source to auxiliary using destination node as the helper. Then move the disk number n from source to destination. Then move n minus 1 disk from auxiliary to destination using source as the helper. This algorithm ensures all the rules are followed. Okay, now let us see the pseudocode of Towers of Hanoi. The function is called as, the function name is Towers of Hanoi. We have the inputs as n, the source node, auxiliary node and the destination node. If n is equal to 1, then we can directly move the disk 1 from source to destination. Then we can stop the function. Otherwise, first we call the Towers of Hanoi function to move n minus 1 disk from source to auxiliary and keep the destination node as helper node. Then we have to print move the disk from source to destination, move the disk number n from source to destination. Likewise, we have to print the statement. Then again finally we have to call the function again to move n minus 1 disk from source to destination, and we have to keep the source rod as the helper rod. Each recursive call reduces the problem size. So this is a very important point. The recursive call reduces the problem size. It reduces the problem size. So this Tower of Hanoi is the recursive function. It again and again call the recursive function. This is called as recursive call. So let us trace the execution of n equals to 3. So let us consider this is the source rod, destination rod, the auxiliary rod and the destination rod. So we have 3 towers or pegs, and we have 3 disks. So first move is we have to move the disk 1 from source to destination. So we have to name this as 3, this is 2, this is 1, and we have to move the first disk from source to destination. This is source, this is auxiliary, this is destination. So now we have to move the first disk from source to destination. So I have moved the first disk. So we have moved 1. Then I have to move the disk 2 from source to auxiliary. So I have to move the disk from source to auxiliary. So this is the second move. Then I have to move disk 1 from destination to auxiliary. This disk from destination to auxiliary. So this is the smallest disk. So this is the third move. Okay, now we have to move the third disk from source to destination. We have to move this disk from source to destination. Now this is the fourth move. Then we have to move the disk 1 from auxiliary to source. Now the source rod is empty. Now we have to move this disk to the source. Now the movement number is 5. Then we have to move the disk 2 from auxiliary to destination. So now this rod is empty. We have shifted this rod to the source, and now this auxiliary rod we have to move to the destination rod. So this is the next move number is it's 6. Now we have to move the disk 1 from source to destination. Now the smallest node is rod is here. Now we have to move that disk to the destination. Now the movement number is 7. Now this is empty. Now the source rod is empty, the auxiliary rod is empty, and all the 3 nodes, 3 disks are shifted to the destination rod. So for n number of disks, for 3 number of disks, we have 7 number of moves. If you have only 1 disk, then you have 1 move. If you have 2 disks, then you have to move 3 moves. Then if it is 3, you will have 7 moves. If you have 4, it's 15. Likewise, it gets increased and it follows 2 power n minus 1 number of moves required to move the disks from source to destination. It means that if we apply 2 power 4 minus 1, so it's 16 minus 1 is 15. We have reached 15 moves. If it is 3 moves, 2 power 3 minus 1. So 8 minus 1, it takes 7 moves. So the minimum number of moves required for Towers of Hanoi is 2 power n minus 1. So the next is time complexity. The recurrence relation for Towers of Hanoi is 2t of n minus 1 plus 1. This means that the function is called twice for n minus 1 disk. So already we have seen the Towers of Hanoi function. So we have called this n minus 1 function twice. So the time complexity is 2 times of n minus 1 plus there is one operation to move the largest disk. We have written this operation, this plus 1 operation as the second point in our pseudocode. So this is the first point, this is the second point, and this is the third point we have written in our pseudocode. So we have called n minus 1 twice and plus 1 operation to move the largest disk. So while solving this recurrence relation, we will get the time complexity as order of 2 power n. This is called as exponential time algorithm. This is called as exponential time algorithm, which means it becomes very slow for large values of n. It becomes very slow for large values of n. Large values of n. This means the exponential time algorithm. So the next is space complexity. This depends on recursion stack. At most, there will be n number of recursive calls in the call stack. So the space complexity is order of n. Okay, let us conclude this Towers of Hanoi. The Towers of Hanoi is important because this is the very best example to understand recursion. Then it helps us to visualize how stacked memory works, and it is very commonly asked in your interviews. So many recursion problems are based on the same logic. Thank you.